and you made zinc chloride, which for the most part just left it behind, aqueous-ish. Okay. So this is what happens when acids encounter metals. They tend to release hydrogen gas, and then make something else. And if you remember your activity series from up here, you can't see it because it's super small and it's dark, but anything above H2 on the activity series will react with acids. So this is why we knew that the acid that Brent's would react because aluminum is way up there next to magnesium and manganese. So yeah, so any metal that is above hydrogen in the activity series will react with acids and release H2 gas. I think, you know, actually, hey, look, there it is. I've got it written down. It's there, it's right there. There it is. Okay. Okay, questions? Moving right along. Bases. Properties of bases. Okay, so bases, they feel slippery, they taste bitter. Soaps still retain some of their basic properties. You need a base to make soap, and soaps tend to retain their basic properties. A lot of cleaning solutions are bases. Okay. And this one's nasty because they are hydrophilic. When we use bases, and we will use bases in the next lab quite a bit, we got to make sure we wear our glasses, because if a base gets in your eye, it's going to immediately start attacking the fluids in your eye, and you don't want that. You want your eye to stay mostly round. A raisin does you no good. Yeah. No eye raisins. Oh, well, it went off the edge.
Close enough? I'll take it. It's very funny.
Yeah, it went off. I tried to adjust it so it wouldn't go into the logo, but here we are. So, not bad for a first attempt. Or second or third, depending. Okay, and bases turn litmus paper blue. Bases turn blue. Bases turn blue. Bases turn blue. Bases turn blue. Bases become blue. We're also going to use an indicator called universal indicator, which is a mixture of several indicators. Indicators change color with acidity or basicity, and universal indicator also turns blue in the presence of a base and turns red in the presence of an acid. Pretty nice. Okay. Can you even solve the word riddle? What is this?
Sodium chloride.
Salt. Yeah, sodium chloride. It is a salt. And what is this? Yeah. So sodium hydroxide is a base, and salt is, or NaCl is a salt. A salt on base, or base under a salt.
My goodness.
I got a million of them. Actually, I only have like 3. But so yeah, base under a salt, or a salt on the base.
You've been waiting 4 years to tell that joke.
Yeah. Finally, I can finally tell it again. Okay, so there we go. Okay, any questions about bases? And we move on. Okay, so common acids. So this is carbonic acid. Oh, something to fix. Okay, so this is something that I need to fix for chemistry AP. That arrow should not be there. That arrow should be a double-headed equilibrium arrow. Because carbonic acid is not a strong acid. It is what we call a weak acid. Okay. Again, I'm jumping around a lot because it's AP. So carbonic acid, H2CO3, this is what forms when you pump carbon dioxide into water. In your mind's eye, you actually might be able to see, oh yeah, carbon dioxide. I can kind of see that. H2O, and then there's a carbon and 2 extra oxygens. Okay, yeah, when carbon dioxide sticks to water molecules, you get carbonic acid. Carbonic acid is what we call a weak acid. It does not dissociate completely. What does that mean? Well, if you put a billion carbonic or H2CO3 molecules in solution, If you put 1 billion molecules in solution, you're probably only going to have 1 million H pluses and 1 million HCO3s. And you'll have 999 million molecules. Whereas previously, with salts, you put NaCl in solution, for every NaCl, you get 1 Na and 1 Cl. You put 1 billion NaCls in solution, you get 1 billion Nas and 1 billion Cls. Not the case with a weak acid or a weak anything. A weak anything basically means it dissociates only partially, and there are a lot more molecules present than ions. Does that idea make sense? So instead of it going, we have waterproof, we have waterproof, we have waterproof, it's like, we have water, we have water, we have water, we have water, we have water. And then finally one goes, poof. Okay. So most of the things that are weak acids stay molecules and do not dissociate. Does that idea make sense? And we're going to spend a lot of time on weak acids because weak acids are the crux of things. How about a strong acid? Oh, this is another weak acid. Darn it. Equilibrium again. So acetic acid's vinegar. And again, if you take a cup of vinegar, the vast majority of the acetate, the vast majority of the things in the vinegar are molecules. Far more molecules than what we call the acidic anion. These are called the acidic anions. Remember cations and anions? Cations are positive, anions are negative. Negative ion. An anion is a negative ion. So the acidic anion comes from the acid. But if you look at a bunch of acetic acid, there are a lot more molecules than there are acidic anions. Now, stoichiometry does play a role in that if you have 1 million of these, you have 1 million of these. Okay. So regardless of what's on this side of the equilibrium, this is stoichiometrically relevant. For this, there's the same number of ions of H pluses as there are the anions. Make sense? Cool. Should we move on? Now for a strong acid. Okay, hydrochloric acid. Hydrochloric acid is a strong acid because it disassociates effectually completely. Like NaCl. Na splits into Na and Cl. You put hydrochloric acid in solution, Gesundheit. You put 1 billion molecules in solution, you're getting 1 billion effectually H plus, and you're getting 1 billion effectually Cl minuses. I say effectually because it's not exactly perfect, as nothing ever is in chemistry. There's always exceptions. Yeah, we just say, it's a strong acid, disassociates completely. Thumbs up if this makes sense to you. Okay. Wave your hand around if you have questions. I'm lost. Okay. Want to go over it again, or do you have a specific question?
Is that in equilibrium also?
No. This is a reactants to products. If I put an HCl in solution, I get an H and a Cl. It disassociates completely. I put an H2CO3 and an HC2H3O2 in solution. There's a pretty good chance it's going to stay HC2H3O2. Every now and then, it might split into an ion, but it's going to stay molecules mostly.
So can you tell by the reaction, like if it's weak or strong, or you have to kind of know?
Both. You can know, and you can tell. Here's the cool thing about the College Board. The College Board says there are 6 strong acids. That's all you have to remember, what those 6 are. And we'll also learn why we consider them strong acids. But there are only 6. Would you like to know what they are?
Yeah.
Okay. Here's 3 of them. Sulfuric acid, nitric acid, hydrochloric acid. And then there are 3 more. HCl, HBr, and HI. Alright. And besides those, there's also this HClO1, HClO4, whereas O is actually made up of 4 O's. HClO4.
What's that one called?
Perchloric acid.
Perchloric acid?
Perchloric acid.
Do you have any of that?
No. I have hydrochloric, I have sulfuric, and I have nitric, but that's all I got. I don't have any bromic or iodic.
And so is the most dangerous the
Yeah, so again, the College Board says there are 6 strong acids, and we just assume a strong acid disassociates completely. But here's the weird thing. According to the rules we know and are learning, Taylor will stay awake, hopefully, there is stronger strong acids. Stronger strong acids. The strongest of the strong acids is perchloric. Sulfuric's pretty strong, so is nitric. Hydrochloric is actually the weakest of the strong acids. And here's what something's kind of bonkers. I, hydroiodic. Br, hydrobromic. HCl, hydrochloric. However, hydrofluoric is not strong. Hydrofluoric is a weak acid. It's extremely dangerous weak acid, but it's still a weak acid.
How is it extremely dangerous weak acid?
Because the fluorine ion, not because of its not because of its acidity, because the fluorine ion is nasty. Because it is so electronegative, it can attack anything. Okay? So hydrofluoric acid is actually not a strong acid. It's a pretty robust weak acid. So what do you notice in the trend? If HClO4 is a strong acid, H2SO4 is a strong acid, HNO3 is a strong acid, and then this is strong but less strong, and this is strong but the least strong. What do you notice about the anions?
It goes down the periodic table.
And what do you notice about the anions? I drew it like this for a reason.
They all need one more thing to
Think about being 6 and going to the teeter-totter.
They're all on those all those weights.
They have more.
I drew it this way for a reason. The stronger or the bigger your acidic anion is, the stronger your strong acid is going to be. Okay? In other words, the more electronegative, big, fat, I want that proton, I want that electron, your acidic anion is, the stronger your strong acid is going to be. I'll print out a table for you later on. You can see the progression. Yeah.
I wrote 5 of them and I don't know which one I'm missing.
Okay, so you got HCl, HSO4, and HNO3,
Yeah,
HBr and HI,
yeah.
HClO4,
Okay,
What's
HCl.
that one called?
perchloric acid. There is chloric acid, chlorous acid, hypochlorous acid, but we'll get to the naming later. Yeah.
Do you remember, do you ever watch MacGyver as a kid?
Uh-huh.
So do you remember that really old school episode where like acid had spilled somewhere and they're gonna like pump lye down there? They're like,
Yeah,
and
individual episodes can't go there. So yes, I remember it's terrible. It's like you go back and like you had fond memories. You try to watch them again, you're like, it just hurts to watch. Okay. So again, strong acids. The more polar an acid, the stronger it will be. In other words, the bigger the fat end, the bigger the big electronegative end is, the stronger it's going to be. Strong acids dissociate completely. So perchloric acid has a monster electronegative acidic anion. Big, huge end. Hydrochloric, it's still pretty negative, but not as negative as bromic or iodic. Yeah.
have you ever used
Perchloric acid? Nope. I have not. I've just used chloric, nitric, sulfuric.
What do they use it for?
Probably something in industry when you want to make a metal do what you want it to do, but I can't say for sure. Okay, so acids can be monoprotic, diprotic, or triprotic. The diprotic and triprotic are called polyprotic acids, meaning they have more than one proton to give up. So diprotic have 2, triprotic have 3. Together they are polyprotic acids. Write that down. Now, that's important for a very specific reason. H2SO4. This is the acid that's hanging out in your, that acts as the electrolyte in your car battery. And this is the reaction that hydrochloric or sulfuric acid gives off. Okay. That's step 1. Look at step 2. How many strong acids are there? 6. Is this one of them? Is that one of them? No, it's not. So this is actually a weak acid. So sulfuric acid only gives off a single proton as a strong acid, leaving HSO4 2 minus, oh, HSO4 minus, sorry, HSO4 minus behind. Okay? Now the HSO4 still acidic, but now it is a weak acid that only gives off a single proton in an equilibrium. Does that make sense? So what this means is, if you have HSO4 in solution, you have very, very few and a whole bunch of So ask your neighbor, in solution, if I pour H2SO4 in solution, what ion is most present in that solution? That's your neighbor.
Are they gonna be
I don't know.
All right, time's up. So, if you believe that there is more HSO4 present than SO4 2 minus present, if you believe it's this one, raise your hand. Okay? If you believe it's this one, raise your hand. Oh, some of you are just complete cowards, huh?
Yeah.
I don't even know.
Okay, second.
Okay, so you pour some H2SO4 in solution. Pour it into H2SO4. It is a strong acid that dissociates completely, making HSO4 2 minus.
Yes.
HSO4 2 minus is a weak acid that will continue to dissociate into H plus and SO4 2 minus. Which one is more present? HSO4 minus or SO4 2 minus?
Present at the end,
Yep.
the other one, isn't that?
Yeah, because that's the strong acid.
Because step 1 is a strong acid. This ion, or this molecule, disassociates completely. Once you get here, in a weak acid relationship, are there more molecules or more anions? There are more molecules. So once you get to this point, you put in 1 million of these, I'm going to put in 1 million of those, I'm going to get 1 million of these. Now I have 1 million of these, I'm only going to get maybe 10,000 of these. And the remaining million are going to be 990,000 molecules. Does that idea make sense? Okay, so no. Okay, so H2SO4 is a strong acid. Strong acids disassociate completely.
Then why would it be more show up more just go on
It only splits completely. So the H2SO4 splits into an H plus
And it's still
an
there?
Yeah,
Oh.
absolutely. So there's no more H2SO4. That's gone. So the first step is done. Now you have the second step where you have the HSO4 minus, which could disassociate into H plus and SO4 2 minus, but it is a weak acid, and there's going to be a lot more molecules present, or whatever the first thing is, than the second thing.
How do you know it's a weak acid though?
Because it's not one of the 6.
Okay, so details is weak.
Uh-huh. Yeah.
Can strong acids ever be at equilibrium?
Nope. That's what makes them strong acids. They have to dissociate completely. So as far as the College Board is concerned, there are 6. Maybe if you go to another country, there's 7 or 8. But so as far as the College Board is concerned, there are 6. Everything else is weak. 1 and 2.
What if you're comparing two strong acids?
Then you look at the strength of its anion. The bigger, the more electronegative the anion is, then the stronger that strong acid is going to be. So with perchloric, which is enormous, being the strongest of the 6, and hydrochloric, which is not as big.
Stronger will always be more.
Yeah, but again, the chances that you'll be asked to compare strong acids, very, very low. Most likely you'll be asked to compare strong acids and weak acids. Right.
So since a base dumps protons,
I hear you saying
an
that
acid,
An acid dumps the
an
protons.
acid dumps protons, bases retract. If you put a base into a neutral solution, would it make the solution more acidic?
Yes. Okay. So Brett and I had this conversation before, and I'll address it once I answer Chris's question.
So are all weak acids in equilibrium then?
Yes.
And is that what defines the equilibrium between?
Yes. Yeah. If it dissociates completely, it's strong. If it's in equilibrium, it's weak. Okay. So water is what we call amphoteric, meaning it can act as a base or an acid, and I'll address this more tomorrow. If you put an acid in neutral water, the neutral water behaves like a base. If you put a base in neutral water, the neutral water behaves like an acid. Does that make sense? Because hopefully you can tell that H2O has both H present and OH present. You put a base, which has OH, into water, the water acts like an acid, giving up the H's. You put an H, an acid, into water, the water acts like a base, taking that H. Make sense a little bit? Okay. Questions for Valerie? And, okay, there you go, strongest acid you can use. And I think we talked about that. We talked about proton. Proton is just hydrogen without an electron.
Now we did.
Proton. Okay, strong bases. Okay, this is totally cool. You don't have to memorize strong bases. Strong bases have an OH present. So strong bases have an OH present. Easy.